P block elements. The general configuration of P block elements is NS2 and P1 to 6 electrons, and the 15th group elements are nitrogen, phosphorus, arsenic, antimony, and bismuth, with nitrogen, phosphorus being nonmetals, arsenic, antimony being metalloids, and bismuth being a metal. As we go down the group, in the 15th group, metallic character increases. Occurrence of these elements: nitrogen is found in the atmosphere, 78% of atmosphere, found as child saltpeter as sodium nitrate, and Indian saltpeter, potassium nitrate in the earth crust, found in living organisms as proteins. Phosphorus found in the calcium salt, which is the apatite family, constitute phosphate rocks, and example fluorapatite, found in living cells, bones, found in phosphoproteins, eggs and milk. Arsenic, antimony, and bismuth are found in earth crust as sulfide ores or sulfide minerals. Ionization enthalpy for 15th group elements: the first ionization enthalpy will increase. Highest is nitrogen, and it keeps decreasing as we go down the period. And this is similar to second and third ionization enthalpy as well. Electronegativity of the 15th group elements: electronegativity decreases as we go down the group. It is followed by all these elements. Melting and boiling point: arsenic has the highest boiling point with antimony, bismuth, and phosphorus. We can say for boiling point, first increases up to arsenic, then decreases from arsenic. And as for melting point, antimony and bismuth have the highest melting point, with antimony being the highest, then followed by arsenic, phosphorus, and nitrogen. We can say here melting point decreases down the group. Electronic configuration of 15th group always has half-filled configuration, which is p subshell configuration, provides extra stability. Due to this half-filled configuration, all the orbitals or subshells before p subshell are completely filled with electrons. Physical property: except nitrogen, all other elements of this group show allotropy. Oxidation states: common oxidation states are +3, -3, and +5. -3 is less common as we go down the group because electropositivity increases down the group. +5, due to inert pair effect, also is less common as we go down the group. Example only characterize +5 of oxidation state in bismuth is bismuth pentafluoride. Inert pair effect in p block elements: the ns2 electrons do not tend to participate in bonding for heavier atoms as we go down the group. This is because of high attractions of ns2 electrons due to poor shielding of d and f subshells. Nitrogen oxidation states: 1, 2, and 4 reacting with oxygen. Mostly all states between 1 to 4 will disproportionate to give an acid solution, which is the nitric acid solution, or others. Phosphorus oxidation states: it will also show +1 and +4 in some oxa acids. Most common is +5 and -3. Mostly all other oxidation states will disproportionate to give +5 and -3 state in both alkali and acidic mediums. Arsenic, bismuth, and antimony, they show the most common oxidation state of +3 as it has increasing stability with respect to disproportionation. Only nitrogen has a final covalence of 4 orbitals. Remaining heavier atoms have vacant d orbitals which can participate in bonding, thereby increase the covalence. Anomalous behavior of hydrogen due to small size, high ionization enthalpy, high electronegativity, lack of d orbital, we see nitrogen being able to form a max of two pi bonds, which is with the p orbitals, with small highly electronegative atoms. Heavier atoms elements of the 15th group cannot form multiple p pi bonds because their orbitals are very large and hard to overlap. They also diffuse. N triple bond has a very high bond enthalpy, but N single bond N is much weaker than any P single bond P or other single bond. This is due to intraatomic electron repulsion of the non-bonding electrons, small size and bond angle of the nitrogen. This inability for N to opt to make N bonds reduces nitrogen's catenation tendency. Catenation, the property of atoms to make long chains of compounds bonding to itself and other elements. Anomaly, lack of d orbital, lack of ability to form d pi and p pi bonds, d pi and d pi bonds. Unlike phosphorus and arsenic can act as ligands because of having d orbitals. Chemical properties, reaction with hydrogen, all nitrogens will react with hydrogen as EH3, and ammonia is the most stable. Stability decreases as we go down, with bismuth trihydride being the least stable, as we can observe in dissociation enthalpies. Basicity of NH3 is highest, can easily accept NH3 plus H plus to give NH4 plus. Basicity of bismuth trihydride is lowest, and ammonia is a mild reducing agent, whereas bismuth hydride is strongest reducing agent. Reducing power increases down the group. P block elements tend to prefer low oxidation state as we go down the group, meaning heavier atom prefer lower oxidation states. Reactions with oxygen, mainly two compounds of E2O3 and E2O5 are formed. The higher the oxidation number, the higher the acidity, as lower oxidation number is preferred as we go down the group. Acidity of the oxides decreases down the group. Nitrogen form purely acidic oxides, nitrogen phosphorus, and arsenic and antimony form amphoteric oxides. Bismuth forms predominant basic oxides. Reactions with halogens can form trihalides and pentahalides. Nitrogen cannot form pentahalides due to lack of d orbitals except nitrogen trifluoride. All other trihalides of nitrogen are unstable. All trihalides except bismuth trifluoride, which is ionic, are mostly covalent in nature. Reaction with metals mostly form binary compounds to exhibit -3 oxidation state. Mostly form binary compounds to exhibit -3 oxidation state. Example Ca3N2, Ca3P2, etc. And the next is preparation of dinitrogen. Preparation of dinitrogen. Dinitrogen preparation. Dinitrogen is produced commercially by the liquefaction and fractional distillation of air. Liquid nitrogen boiling point is 77 Kelvin, distills out first, leaving behind liquid oxygen, which is 90 Kelvin. In the laboratory, dinitrogen is prepared by treating an aqueous solution of ammonia chloride with sodium nitrate. NH ammonium chloride plus sodium nitrate gives nitrogen gas, or the dinitrogen, water and salt. Small amounts of nitrogen monoxide and nitric acid are also formed in this reaction. These impurities can be removed by passing the gas through aqueous sulfuric acid containing potassium dichromate. It can be obtained by the thermal decomposition of ammonium dichromate. We will get, if we heat ammonium dichromate, then we will get dinitrogen, water and Cr2O3. Very pure nitrogen can also be obtained by thermal decomposition of sodium or barium azide. Barium azide, BaN3 twice, will give Ba plus 3N2. Azo group meaning nitrogen groups. These are the preparation methods for dinitrogen, which the first method is the industrial method, where they will liquefy the air. Then after the liquefaction, they will do fractional distillation, and because nitrogen has a lower boiling point, first it will be taken out, then which leaves liquid oxygen. In laboratory, nitrogen is prepared by treating an aqueous solution, and this is the first case. In industrial case, large scale. In laboratory, in the small scales, dinitrogen is prepared by treating an aqueous solution of ammonium chloride with sodium nitrate. Treating ammonium chloride with sodium nitrate. And here the aqueous solution is ammonium chloride. Small amounts of NO and HNO3 are formed in this reaction. Basically, the first main reaction is this one, but in this reaction, small impurities like nitric acid and nitro group or NO group, NO is also formed. In this reaction, these impurities can be removed by passing through aqueous sulfuric acid with potassium dichromate, where it seems that potassium dichromate will react with the HN groups and it will form ammonium dichromate. If we heat this, we will get nitrogen, water and Cr2O3. And the third method is by thermal decomposition of azide groups, either sodium or barium azide groups. First method, liquefy air, then fractional distillation, as air's major components, where 78% of air is nitrogen, 21% is oxygen, and the remaining are other gases. Then fractional distillation, nitrogen having 77.2 Kelvin of boiling point, and oxygen with 90 Kelvin, nitrogen will evaporate or vaporized, whereas O2 is left. This is the first method of preparation. In the industrial method, this is in large scale preparation or industrial preparation. The next method is in a laboratory preparation. In laboratories, aqueous ammonium chloride is solution is treated with sodium nitrate, this is NH4 Cl NaCl. We will get gas, meaning this will evaporate. This is aqueous, this is liquid. In the above reaction, small amounts of impurities of nitric acid and NO are formed. They can be purified by passing through H2SO4 aqueous solution plus K2Cr2O7 solution. So Yes. When the second method of preparation is reacting ammonium chloride with sodium nitrite. In this reaction we will get N2H2O, N2 4H2O, no wait, 2H2O, we will get 2H2O and NaCl. In this reaction the impurities of nitric acid and NO will be formed, so nitrogen monoxide. And so to avoid such impurities, or to get rid of those impurities, we will purify it by passing it through a sulfuric acid and a potassium dichromate solution. If we pass it to a potassium dichromate solution, after passing it through this solution, we will get NH4 ammonium dichromate. And this, if we heat or thermal decomposition, of ammonium dichromate will give heating symbol N2 4H2O plus Cr2O3. They didn't mention it as gas here, so I will also not mention it as gas. This is the second preparation method, and the next preparation method for dinitrogen, third preparation method, we can prepare a dinitrogen through sodium azide or barium azide. How is it is through thermal decomposition. When we use thermal decomposition, sodium azide or barium azides are basically BaNH, not NH. This is barium azide. This, if we heat, we will get very pure N2. Reaction is it is 3N2 plus barium. Yes, barium. This is the reaction. not too good. Even though it's whatever. In this equation, no. From this reaction, we get very pure dinitrogen. Maybe they're repeating dinitrogen again so that we don't get confused. Very pure dinitrogen. These are the preparation methods. Now let's see its properties. Dinitrogen is colorless, odorless, tasteless, and non-toxic gas. As it is in air, we can say we are also breathing nitrogen in, as 78% of our atmosphere is of nitrogen only, and nitrogen atom has two stable isotopes of N14 and N15. It has a very low solubility in water. They are talking about the dinitrogen, 23.2 centimeter cube per liter of water at 273 Kelvin and 1 bar pressure, and low freezing and boiling points. Dinitrogen is rather inert at room temperature because of the high bond enthalpy of N triple bond N. It means N2 doesn't react too well because the N triple bond N is a very strong bond, and the energy to break such a bond and form other bonds is really high. Reactivity, however, increases rapidly with rise in temperature. At higher temperature, it directly combines with some metals to form predominantly ionic nitrides, and with non-metals covalent nitrides. A few typical reactions are, but they're saying as temperature increases and as the bond enthalpy decreases, the reactivity increases, and with metals it forms ionic bonds or ionic compounds, whereas with non-metals it will form covalent nitrides. In case of a metal, if you take lithium and dinitrogen and heat it together, it will form lithium nitride. And in case of magnesium, if we heat, it will also form magnesium nitride. These are ionic nitrides. It combines with hydrogen at about 773 Kelvin in the presence of catalyst, Haber's process. This is the basic Haber's process of nitrogen reacting with hydrogen at 773 Kelvin to give two ammonia. The formation enthalpy of this is minus 46.1 kilojoule per mole. Dinitrogen combines with dioxygen only at very high temperature at about 2000 Kelvin. Dinitrogen combines with dioxygen only at very high temperature, about 2000 Kelvin, which is about 1800 degrees Celsius or 1723, to form nitric oxide, NO. N2O2 will give 2NO2. There is no arrow mark here. The main use of dinitrogen is the manufacture of ammonia, may be through the Haber's process, and other industrial catalysts, chemicals containing nitrogen, example calcium cyanamide, Amide is the NH2 group, and cyanamide meaning CN group. Cyanide group is CN. It also finds use where an inert atmosphere is required. Example, because we saw that nitrogen triple bond N is a very strong bond. It is very inert. So in the iron industry or the steel industry, where inert like in where iron, if other gases like oxygen or any such gases is there, it will easily react in very high temperature and form ferric oxides which are useless and not needed. So instead of that, the industry can use nitrogen, which is inert, instead of oxygen. Like we can also use noble gases like argon. Nitrogen is also inert and is used. Inert meaning non-reactive atmosphere is required. Iron steel industry, inert diluent for reactive chemicals. Diluent. Liquid nitrogen is used as a refrigerant to preserve biological materials, food items, and in cryosurgery. What is cryosurgery? Maybe it is transplanting some organs. Maybe it's related like preserving of the organs. Yeah, I believe that is the case. I heard cryopreservation, where we store pollen grains or human semen. So maybe it's related to that. Cryosurgery, a medical process that uses extremely cold, usually from liquid nitrogen or argon gas, to destroy abnormal or diseased tissue. Treat skin lesions, so it seems I'm wrong. Medical process that use extremely cold liquid nitrogen or argon gas to destroy abnormal or diseased tissue. Okay. Freezing causes ice crystals to form inside cells, which ruptures them, leads to tissue death. Okay, I understand. Okay, they gave reactions. The reactions or properties of dinitrogen, which is a colorless, odorless, tasteless, and of course a non-toxic gas. Nitrogen atom which has two stable isotopes, and they said that dinitrogen is very less soluble in water, and it has a low freezing and boiling points. Dinitrogen is rather inert at room temperature because of its N triple bond N. Reactivity, however, increases rapidly with rise in temperature. At high temperature, it directly combines with some metals to form. Okay. They gave about how nitrogen is colorless, odorless, and non-toxic. They gave about how nitrogen has a low freezing and boiling points. They gave about how nitrogen has less solubility in water. They gave about how nitrogen reactivity is very less in room temperature, but as we increase the temperature, the reactivity will continue to increase, and at high temperatures it will react with metals to form ionic nitrides and with non-metals to form covalent nitrides. And As for the Haber's process, they gave that at 773 Kelvin with a catalyst, which is iron, at 773 Kelvin with a catalyst, nitrogen will react with hydrogen to give ammonia. This is what we call the Haber's process. Then next, at a very high temperature of 2000 Kelvin, dinitrogen and dioxygen fuse to give nitrogen monoxide. And as for the uses of this dinitrogen is that, one, it is because it is inert, it is used in places where there is a need for inert atmosphere. It is used in preparation of ammonia, and it is also used as a refrigerant to preserve biological materials, or as well as in cryosurgery. Properties of dinitrogen. Colorless, odorless, non-toxic, very less solubility in water at room temperature and standard pressure, less reactive / inert at room temperature due to high bond enthalpy of N triple bond N. These are the basic properties. Higher it will become reactive at high temperatures. At high temperatures, it will react with metals to form ionic nitrides and with non-metals to form covalent nitrides. Nitrides, I believe, but nitrides. Example, Li plus N2, heat, LiN3. Right, no. Li3N, six Li and 1 and 2 heat will get, and the second reaction of Mg plus N2 heating, we will get Mg3 N2, Mg3 N2, 3 Mg plus N2. These are the reactions. And next is Haber's process. N2 plus H2, Fe as catalyst, 773 Kelvin, and I believe it is 2NH3, 2N, H3, yes, this is the Haber's process. Next, for formation of NO, N2 plus O2 at 2000 Kelvin, very high temperature, will react to give 2NO. And as for this is the properties, and as for the industrial uses or normal uses of dinitrogen, one used to prepare ammonia, NH3. Next, it is and there is one more point which I forgot to write here, that is it has low boiling and melting points and freezing points. Okay, that is the case. And it is inert, used to prepare ammonia. As it is inert, it is used in steel, iron industries to provide inert atmosphere and for no. And due to same reason as a diluent for reactive chemicals. These are the uses of nitrogen. and there is also and other N compounds. Liquid nitrogen is used as a refrigerant for material storage and also used in cryosurgery. Okay. These are the uses of dinitrogen. Next, write the thermal decomposition of sodium azide. It is NaN3 gives 2Na plus 3NH2. It is exactly same as Bn3 twice. Wait, barium had or we can use here NaN3 decomposition gives 2Na plus 3N2. This is a sodium azide reaction. Why is N2 less reactive at room temperature? Because of the high bond enthalpy. Maybe at high temperatures it will gain energy, and due to that it can easily break the bond. Next is preparation. Next is about the compound of ammonia. The preparation of ammonia. Ammonia is present in small quantities in air and soil, where it is formed by the decay of nitrogenous organic matter. Example, urea. This is the urea compound. N2CONH2 plus water will give NH4 twice CO3, diammonium carbonate. Which again dissociates into ammonia, water and carbon dioxide. On a small scale, ammonia is obtained from ammonium salts, which decompose when treated with caustic soda or calcium hydroxide. What is caustic soda? I think calcium. Sodium hydroxide, okay. NaOH is also called as caustic soda. We can either treat it with sodium hydroxide or calcium hydroxide. With ammonium chloride plus COH twice will give 2 ammonia 2H2O plus CaCl2 And in case of caustic soda, which is sodium hydroxide reaction, it will react with NH4 twice, SO4, ammonium sulfate plus caustic soda will give 2NH3 plus 2H2O plus Na2SO4. On a large scale, ammonia is manufactured by or through Haber's process. It is N2 plus 3H2 gives 2NH3. This is the formation enthalpy is minus 46.1 kilojoule. In accordance with Le Chatelier's principle, high pressure would favor the formation of ammonia. The optimum conditions for the production of ammonia are pressure of 200 into 10 power 5 or 2 into 10 power 7 Pascal, about 200 atm, because 1 atm is around 1.01 into 10 power 5 Pascal. It is converted into 200 atmosphere. It is actually a bit more than 200 atmosphere. A temperature of 700 Kelvin, which is 773 Kelvin exactly, and the use of a catalyst such as iron oxide with small amounts of K2 potassium oxide and aluminium oxide to increase the rate of attainment of equilibrium. The flow chart for the production of ammonia is shown in fig 7.1. Earlier, iron was used as a catalyst with molybdenum as a promoter. This is the flow chart for manufacture of ammonia. I will read it. And they gave a total of 3 preparation methods, with 2 being small scale preparation methods and 1 being large scale preparation method. The first is ammonia, which naturally is produced or formed in small air or soil, where it is formed by decay of nitrogenous organic matter, which is urea, or example is urea, where urea will react with water to give ammonium carbonate, which will again decompose to give ammonia, water and carbon dioxide. On a small scale, ammonia is obtained from ammonium salts which decompose, and the second one is decomposition of ammonium salt, which decompose when treated with caustic soda or calcium hydroxide. Calcium hydroxide is also called as slaked lime, and CaO, calcium oxide, is called as quicklime. Anything related to lime? It might be calcium, where NH4Cl plus calcium hydroxide, which is ammonium chloride with calcium hydroxide, will give ammonia, water and calcium chloride, and ammonium sulfate will react with caustic soda to give NH3, ammonia, water and Na2SO4, sodium sulfate. Salt plus base gives ammonia, salt and water. On a large scale, it is Haber's process, where the formation enthalpy is minus 46.1 kilojoule per mole, and with Le Chatelier's principle, the more amount of the more the pressure on the left hand side of the equation, basically N2 plus H2 gives ammonia, the more pressure on this side, the more the reaction will go forward direction. So a pressure of approximately 200 atmosphere is used, and at temperature of 773 Kelvin, and the use of catalyst as iron oxide with small amounts of potassium oxide and aluminium oxide is used to increase the rate of attainment of equilibrium. it is a latest, or at least the new process is to use iron oxide, which is the ferric oxide. So iron oxide with small amount of K2O, potassium oxide, and aluminium oxide. This is normally used as a catalyst in the new times, or the new method. But before, catalyst was iron, and molybdenum acted as a promoter. And let's see the flow chart. Hydrogen and nitrogen are pumped through two tunnels or two pipes, and compressor, meaning it will compress those two gases together with a pressure of 200 megapascals, or 20 megapascals, or approximately 200 atmospheres of pressure. Wait. I believe it is 200 megapascals, not 20 megapascals. So one more zero here. 200 megapascals compressor, which will, this seems to be an equilibrium, where first it will be compressed, then N2 plus H2, one way it comes from these pipes where it is getting compressed, and the another way it comes from the liquid ammonia, and it both are mixed, and with a catalyst of iron oxide, aluminium oxide, and potassium oxide at 700 Kelvin, all these mix to form liquid ammonia. This is the flow chart. Preparation of ammonia. First method, naturally small amounts of NH3 is found in air, soil, formed via decomposition of organic matter or nitrogenous matter. Example, urea. This reaction is ये ammonium carbonate, This is urea, water, ammonium carbonate, then this will react to give NH3 plus water plus CO2. The balanced reaction is 2NH3, where NH3 ammonia is finally produced. And the second method of preparation, small scale preparation of NH3, is through ammonium salts reacting with caustic soda, sodium hydroxide, or calcium hydroxide. The reactions are NH4Cl plus CaOH twice gives NH3 water and CaCl2. And second reaction, NH4 sulfate plus 2NaOH will give NH3 water plus NaSO4, Na2SO4. Where here it is 2, 2 and 2. Here it is 2 and 2. Yes. Now these are the small scale preparation. Third method, large scale preparation of ammonia is through Haber's process. Haber's process, of course. Now Haber's process, which according to Lee Chartlier's principle, favors formation of ammonia in high pressure of reactants. The pressure required is 200 atms, 200 atm or 200 megapascal of pressure with 773 Kelvin is 773 Kelvin of temperature. And the apparatus, the catalyst earlier was iron and molybdenum as a promoter. Now iron oxide and small amounts of potassium oxide and aluminium oxide are being used as catalysts.